Okay, let's take a look at some of the mathematics involved in a wave. Here we have a transverse wave on a string. This is very similar to what we're going to be doing in lab when we do the standing waves. As this mechanical device oscillates back and forth, it transfers energy to the string vibrates up and down. Now, if we want to talk about the maximum amount of displacement from equilibrium, we call this amplitude, okay? Amplitude is either our maximum value or our minimum value. It's how tall the peaks are, how deep the valleys are. Remember, this center line, this white line, is equilibrium, okay? So amplitude is the maximum displacement from equilibrium if this is a physical wave. If it's an electromagnetic wave, where we have an electric field and a magnetic field, then my amplitude would be the maximum electric field or the maximum magnetic field. If it's a sound wave, we could use pressure, the maximum pressure or the minimum pressure of a sound wave, or the maximum density or the minimum density of a sound wave. But again, the amplitude can be visualized as the height of a peak or the depth of a trough. How far from equilibrium do we go? The wavelength represents how often does this wave repeat itself in space. Now, it's important to understand that we need a periodic wave in order to identify some wavelength, okay? In this case, we've got a nice periodic wave generated by a little oscillator. So it simply repeats itself over and over again in time and in space. Now, if I measure the distance from one peak to the next peak, that is the wavelength. And we use the symbol lambda, it's a Greek letter L, to represent wavelength. Now, later on, you're going to come across another constant. Well, it's not really a constant, another quantity. This quantity is known as K, and sometimes it's called the propagation number. It has a number of different names, but it is related to lambda in terms of where lambda asks what is the distance between peaks. K is sort of related to, but not directly, how many peaks do we have per given distance. So again, we'll come across that later on. Now, for a wavelength, if the wave is vibrating very, very quickly, the wavelength becomes small, okay? So if I were to take this little oscillator and I make it oscillate faster, we might get a wave that's much smaller than that, and a wavelength that, where the peaks come together much closer. If I were to slow the oscillator down, and it would oscillate like this, then the wavelength would become longer. So generally, increasing the frequency will drop the wavelength, or the wavelength will become smaller. Decreasing the frequency makes longer wavelengths. Now here are some selected waves, okay? On the right, we actually have the entire electromagnetic spectrum. On the left, we see that sound waves that you can hear, audible sound waves, these are from 20 hertz to 20,000 hertz, as we'll find out in the next chapter. They have a wavelength between 1.7 centimeters and 17 meters. So that's a pretty large difference in terms of the overall physical length. For light, which we can see, electromagnetic waves, we can only see from about 0.39 microns, or 300 nanometers, to about 780 nanometers, or 0.78. So that's this part of the spectrum right here, right in here, okay? That's our visible light. Here we can see that for other parts of the electromagnetic spectrum, in terms of gamma rays, they can be extremely small, okay? Here it shows 10 to the minus 6 nanometers, okay? 10 to the minus 6 nanometers. Well, already a nanometer is 10 to the minus 9. So these gamma rays, which are very, very high energy, can actually be about the size of a nucleus, or about 10 to the negative 15 meters across. Now we get down into the X-ray part of the spectrum, where we're down to about a tenth, or about a nanometer, okay? Again, as we said before, that's 10 to the 9. Ultraviolet light is about 100 nanometers. Of course, the range is larger than that. Visible light, approximately a little less than a nanometer. I'm sorry, 100 nanometers, a little bit less than a micron. Infrared, measured in microns. Microwaves measured in centimeters, and then radio waves measured in meters. So you can see for a lot of these phenomena, there can be a huge range in the wavelengths. In fact, the longest radio waves can be measured in hundreds of kilometers. So that's 10 to the 5th all the way down to 10 to the minus 6, just on this chart. Okay? Yeah, represents about 11 orders of magnitude. Okay. One way of looking at a wave is to visualize it like this simple harmonic oscillator. We have an oscillation, but this oscillation can propagate. Instead of a single mass sitting on a spring, we have many parts of a medium which are oscillating back and forth. Okay? Now, the period at which any point in a medium, let's say right here, oscillates back and forth, okay? This is a little bit different than our graph where we're graphing as a function of position. Here we're showing amplitude, we're showing displacement as a function of time. The time it takes any particle or any point of a medium, I shouldn't say particle, any point of a medium to return to its original position after a wave passes through, or return to equilibrium after a wave passes through, that is equal to the period. So here we can see from peak to peak, yeah, takes about 0.45 seconds, or the distance from valley to valley. Now, frequency is inversely proportional to period. We've seen that already. The longer the period becomes, the lower the frequency. So here's a high frequency wave. We can see that the period is very, very short. Here's a low frequency wave. We can see that the period gets longer and longer. And again, this is just a simple inverse relationship that we talked about when we talked about oscillators. So frequency and period are the inverses of one another. Frequency is measured in hertz. And just some different examples here. Humans can hear from 20 hertz to 20,000 hertz, but the frequency that we hear the best is 4,000 hertz. If we want to calculate the period from that, we just take 1 over 4,000. Here we can see hertz is 1 over a second, okay? So we take 1 over 4,000 and we get 0.00025 seconds, or a quarter of a millisecond, or 250 microseconds. So this is telling you two things. One, is telling you that this wave is oscillating 4,000 times per second. It's also telling you that each oscillation takes 250 microseconds to take place. Now, AC power oscillates with a period of 0.0167 seconds, okay? what if I want to convert that into frequency? In the previous case, we took a frequency and converted it into period. Now we're going to do the reverse. Once again, all we need to do is take the multiplicative inverse. 0.0167, if we take the inverse, is 60 hertz. Sometimes this is called 60 cycle. So here we can see the relationship between frequency and period. We use SI units, so we don't do a lot of switching with the metric prefixes. But clearly you can see if we have a period of 10 to the, 3 hertz or 1 kilohertz, that corresponds to a period of 1 millisecond or 10 to the minus 3 hertz. A megahertz, a microsecond, 10 to the 6. You take the inverse, it's 10 to the minus 6. A gigahertz, 1 nanosecond. A terahertz, 1 picosecond. Again, frequency and period, these are just inverses of one another. Now let's get to a speed of a wave. The speed of a wave is equal to the wavelength times the frequency. Now we can actually show that this makes sense dimensionally. The SI units for velocity are meters per second, right? We know that for wavelengths, wavelength is measured of distance, so it's meters. And for hertz, hertz are 1 over a second. So dimensionally, this equation makes sense, okay? Now, it's important to understand that for any wave, the velocity of the wave is related to the properties of the medium, okay? It is really the properties of the medium that govern velocity. So when we disturb a medium at some particular frequency, the velocity and the frequency are going to determine what the wavelength is, okay? So, it's not the tail wagging the dog here. Medium determines velocity, okay? How you create the waves in terms of frequency will then correspond to a particular wavelength. Okay, let's take a look at this. At a certain temperature, sound will propagate at a speed of 343 meters per second, okay? Next chapter, we find out that temperature is a big controlling factor in how fast a wave travels, okay? The higher the temperature, the higher the velocity. All right, now with that in mind, let's say that we have a sound wave with a wavelength of 3 meters. What frequency is the wave? All right, so we start with this equation right here. We want to solve for frequency. So we take both sides and divide both sides by wavelength. That gives us frequency is equal to velocity divided by wavelength. 343 meters per second divided by 3 meters. Meters cancel out with meters. Hold on. Meters cancel out with meters. We're left with 1 over seconds. 343 divided by 3 is 114. And that's the frequency of the wave. Likewise, if you take light and do the exact same thing with it, okay, light in a vacuum travels at 3.00 times 10 to the 8 meters per second. Let's say that it has a wavelength of 3 meters. What is its frequency? Now, the faster the wave goes, the higher the velocity, okay? The higher the product of the wavelength and frequency. So for a very large wavelength, we're still going to get a fairly high frequency just because the velocity is so large. Frequency is velocity over wavelength. For light, travels at 3 times 10 to the 8 meters per second. And even at 3 meters, the frequency is extremely high. 1.00 times 10 to the 8 hertz, or 100 megahertz. This would be an FM radio wave at 100 megahertz. Let's calculate wavelength from velocity and frequency. Here we have our sound wave again, traveling at 343 meters per second. We have a 4,000 hertz sound. We recognize this 4,000 hertz as the sound wave that humans can hear the best. We solve for this from the original equation. We take V equals wavelength divided by frequency. I divide both sides by frequency. I get wavelength is velocity divided by frequency. So I do my calculation. I get 0.0858 meters, or this wavelength is 8.58 centimeters. Okay, now we go to light. Much higher velocity, much smaller. Much higher velocity. We'll see how this affects it. Here I have a light wave traveling at 3 times 10 to the 8 meters per second again. Okay, this time I'm going to go to a very, very high frequency. Okay, this is 500. If you want to do the conversion, this is 500 terahertz. Okay, think about the metric prefixes here. 10 to the 3 is kilo, 10 to the 6 is mega, 10 to the 9 is giga. So we're all the way up to tera at 10 to the 12, 10 to the 14 is 100 terahertz. So this is 500 terahertz. Okay, I want to know what that wavelength is. Okay, so I use my equation. Velocity equals wavelength times frequency. Here the wavelength is equal to velocity divided by frequency. And 10 to the 8 divided by 10 to the 14 gives me 10 to the minus 6. But we have 3 divided by 5, which gives me 0.6. So that becomes 6 times 10 to the minus 7. Okay? Now, why is this important? Well, 600 nanometers is actually yellowish orange light. You can see from 390 nanometers, okay, that's the edge of the violet part of the spectrum, almost getting into the ultraviolet, all the way to the red edge, which is 780 nanometers, okay? So this fits right in that range that we can actually see. And again, that's oscillating at an incredibly high frequency, okay? Now also this is important because when we think about microscopes, you can never image something smaller than the wavelength of what you're using. So it's 600 nanometers, which is, approximately 1 micron. This means that the best resolution that you'll ever get from an optical microscope is going to be roughly about 1 micron. Even the best microscopes optically don't achieve that. Okay, so what have we talked about so far? We've talked about period, the time it takes one oscillation to take place. We've talked about frequency, the number of oscillations that take place. We've talked about wavelength, the distance that the wave takes to repeat itself. And we're going to introduce 2 new things here. Well, one's not really new. Omega is the angular frequency, okay? We saw that for rotational motion in physics 1. And K will be connected with lambda, like we said earlier. All right, if I want to create a function of both position and time, and this is in 1 dimension, folks, but if I want to create a function of both position and time for a harmonic wave, the simplest type of wave that I can make, that function would look something like this. Now let's take a look at what's in here. Originally, when we looked at the simple harmonic oscillator, it looked something like this. X is equal to A, cosine or sine, I'll use sine here, sine omega t, okay? So that would be my little oscillation just sitting there, not propagating, just sitting there, vibrating up and down, okay? So that's this term right here. It allows the wave to basically oscillate with respect to time. But notice I've added a new term here. I also have this kx. If omega t allows it to oscillate in time, kx allows it to oscillate in position. So here, k is related to lambda by this 2 pi, just the same way that angular frequency is related to period by 2 pi. If period represents the time it takes for one oscillation to take place, lambda represents the distance for one oscillation to take place. So k is sort of the analogy in position of what omega is to time. Okay, so as we make the wavelength go up, k goes down. As the wavelength gets smaller, k is going to get greater. All right, but again, if I were to plot this and I kept using new times, like this is the original wave, and then I would enter some t at a later time, I would see the wave has moved forward. Okay, so that's a nice thing about that function right there. Again, it's the simplest type of wave, either a sine or a cosine. It is a component which causes it to oscillate in position. It's a component that causes it to oscillate in time. So this is what would look if I graph it, okay? Once again, this is slightly different than what we've seen earlier. We changed the plus sign to negative here, and what this is going to allow it to do is oscillate in the positive x direction, okay? Actually, what you're seeing here is at a later time. Originally, if I graph this, it would look something like this. See if I can get this. I usually have such a problem drawing this, okay? This would be a t equals 0. This would be it. The black line would be at some other time. But again, if I have a negative sign right here, it causes the wave to propagate in the positive x direction. If I switch the sign to positive, the velocity is in the negative x direction. Okay? But both represent waves. That just makes it a little bit, well, it has to do with the harmonic functions themselves, but you just think of this sign right here, it'll be the opposite in direction. And again, here we're plotting different waves. Let's set, in each case, t equal to 0, because we can't show time and position at the same time in these graphs. But you can see here's a k value of 1/2, okay? We got to put units in here too. This would be inverse meters. Here's a k value of 1. And here's a k value of 2. See what's happening? The wavelength's getting smaller. We know that k is equal to 2 pi over the wavelength. And as the k gets larger, the wavelength gets smaller. The number of peaks that we have for a given distance gets larger and larger. Okay? Yeah, one way I used to think about this is omega was the angular frequency. It's just 2 pi off from being the linear frequency. Where that represents the frequency in time, k is almost like a frequency in space. And again, here are different values of K. Of course, if we change our graph, notice that we change from distance to time. As omega gets larger and larger, the number of oscillations per second get larger and larger. So we're not going to do a lot with these waves or these harmonic waves, but you can see how they could be used in different applications, like sound waves. We could talk about pressure as a function of distance and time, where P0 represents the amplitude of the pressure. In this case down here, we have both the electric field and the magnetic field. Oscillating in time, E0 or E naught would be the maximum electric field. B naught would be the maximum magnetic field. If you ever get into quantum mechanics, we talk about something called the wave function. Probably talked about this when you got into chemistry. We talked about s orbitals, p orbitals, and d orbitals. Okay. This little psi right here is connected with all kinds of properties of quantum mechanical particles. It's known as the wave function. Okay. And we can use it to determine the most probable point. Let's say an electron would be around the atom. So once again, if this were just a particle wave traveling, let's say an electron in an electron microscope, we could express the wave itself like this. And of course, we know with electron microscopes, we're looking at very, very small things. So in order to see small objects, we want a small wavelength or a very high K for that. Okay.